In this section, we'll be talking about graphs of quadratic equations. And as a reminder, quadratic functions have this form, f of x equals ax squared plus bx plus c. So you can spot them based on the fact that the highest power in the function is 2. So 2 is the highest power. So that's what makes it quadratic. So these are degree 2 polynomials. And the graphs of any quadratic function are going to be a shape that we call a parabola. So looking here in this introductory example, this is an example of a parabola. So here we're looking at the function f of x equals x squared minus 4x plus 5. So you can see the graph here on the notes, but let me go ahead and graph that in my graphing calculator as well. So under y equals, I'm going to do x squared minus 4x plus 5. And let's take a look at that graph. Okay, and if I use my trace function, I can identify a few of these key points that are labeled on our paper graph. So for example, when I hit trace, if I type x equals 0, I get y equals 5. So we can see the ordered pair 0, 5. I can see the ordered pair for x equals 4, y also equals 5. And then at x equals 2, I see the ordered pair 2, 1, right? So this is just kind of our regular vanilla form of our quadratic functions, but we could convert this into what's called a standard form for graphing. And this second version of our function is pretty useful because we can look at it pretty quickly and do a nice quick sketch of our graph a little more easily than we can with the first function, especially if we don't have our graphing calculator with us. So if you take a look at this standard form of the same function, f of x equals x minus 2 squared plus 1. I just want to verify that those actually are the same functions. So one way I can do that is under my second graph, I'm going to graph this in standard form. X minus 2, close the parentheses, squared plus 1. And you can see that that red graph appeared directly on top of that blue graph. So they're the same functions. Algebraically, if I FOIL x minus 2 squared, that would give me x squared minus 2x, which would total to minus 4x. And then negative 2 times negative 2 would be plus 4. And then when I add the one that I already had, this gives me f of x equals x squared minus 4x plus 5, which is that original version that we started with. Okay, so why do we bother with this standard form? What's so great about it? One thing is we can quickly pull out the vertex. So if we think of our kind of standard parabola as f of x equals x squared, I'll graph that in my third equation here. So that's the parabola that passes through 0, 0, the origin. If we think of our transformations from earlier sections, you can see that the x minus 2 in parentheses produces a shift to the right 2. So leaving the origin, that shifts us to the right 2. And then that plus 1 in the equation shifts us up 1. So we go through what's called the vertex. The vertex, which in this case is the ordered pair 2, 1. And just looking at the equation, the x minus 2 squared tells us that our x-coordinate in the vertex will be 2. The plus 1 at the end tells us that our y-coordinate will be 1. So we'll talk about that more in depth later on. But that's one example of a quick, easy way that we can look at the corresponding graph given the function. All right, so we just showed how to go from standard form to that original form. What if we want to go in reverse? So suppose that we have y equals x squared minus 4x plus 5, and I want to convert this. To that standard form that we saw. So I could do this by using our completing the square techniques that we've used in previous sections. So remember, for completing the square, we take b over 2 and square it. In this case, b is negative 4. So that's going to be negative 4 over 2 squared, which is negative 2 squared, which gives me positive 4. So I started off with y equals x squared minus 4x plus 5. And I'm going to add that constant plus 4 so plus 4. Because I'm staying on the same side of the equation, this is different from what we did in earlier sections, so I'm going to use completing the square, but I want to balance the equation keeping my constants on the same side. So I'm going to put a plus 4 and a minus 4. So I'm not changing that equation, right? The right side of the equation has the same value because I'm adding 4 and subtracting 4, right? But now what I'm going to do is I'm going to focus just on these first 3 terms, that first trinomial. X squared minus 4x plus 4 would factor as x minus 2 times x minus 2, and then I still have the plus 5 minus 4 on the outside. And of course I can write this as x minus 2 squared, right, with that squared exponent, and then 5 minus 4 gives me a plus 1. So that's how I get to that standard form, by using completing the square techniques. Okay, so let's start picking apart this specific function. So let me clear this guy out, and I'll clear that out because they're the same ones. So we've just got this graph of, in this case, f of x equals x minus 2 squared plus 1, or its equivalent, f of x equals x squared minus 4x plus 5. So let's pick apart that graph, but let's use the standard form. So in standard form, we could think of our function as f of x equals, and I'm reading right here, a times x minus h squared plus k. So a would be any coefficient out in front of the parentheses. For our function, we don't have anything out there, but we could think of a equaling 1, right? So a equals 1 for our particular function. And our rule for the direction of the opening is if a is positive, then the way I think of it is our parabola looks like a smiley face. So if you want, you can do boop, boop. So it looks like a little smiley face. If a is negative, then our parabola is going to be downward facing, and it looks like a frowny face. Cheesy, but hopefully it'll help you remember. So in our case, we have a equals 1. That's a positive number. Positive smiley face, our parabola opens upward. All right, the vertex that we talked about, we already identified it. We can see using the trace function or our paper notes that the vertex is that ordered pair 2, 1. So we already know this. From the function, we can see that our vertex is going to be hk, the ordered pair hk. So x minus h, in this case x minus 2 gives us 2 for our x coordinate. And then the plus 1 at the end of our function gives us the y coordinate 1. All right, so x will be the opposite sign, the y will be the same sign. So x minus 2, we have a positive 2, plus 1, we have a positive 1 in our vertex. All right, our axis of symmetry. Whatever your x coordinate is in your vertex, that's going to correspond to your axis of symmetry. So in this case, our x coordinate was 2, our axis of symmetry is x equals 2. If you're asked for an axis of symmetry, do not say, oh, it's 2. That's just a constant, right? That's not an equation. So when we say an axis of symmetry, that's represented, and we can see it here, it's represented by a dashed vertical line. So here on the graph, this is our axis of symmetry. And in this case, the equation for the axis of symmetry is x equals 2. So whatever the x coordinate is in your vertex, x equals 2, that's your axis of symmetry. And the reason that we mention our axis of symmetry, if we know, for example, that our y-intercept is 0, 5, then that's 2 to the left of our axis of symmetry, right? At x equals 2, if I go 1, 2 to the left at x equals 0, I have 0, 5. So if I go 1, 2 to the right at x equals 4, I can see I also have that matching symmetry point 4, 5. Okay, so we always have matching points across that axis of symmetry. All right, next up, our x-intercept. Visually, we can see that our entire parabola floats above the x-axis, so there's no x-intercept. If we wanted to establish this algebraically, we could set our function f of x equal to 0. So in our case, and I'll just show my work over here, we would set x minus 2 squared plus 1 equal to 0 and attempt to solve for x. I would subtract 1 from both sides, and this gives me x minus 2 squared equals negative 1. And at this point, I can actually see that this isn't going to work out. If I square any real number, I'm not going to get a negative 1, right? So in that case, we'd have to verge into imaginary territory. If I keep this going, though, if I took the square root of both sides, I'd have x minus 2 equals plus or minus, and we learned before that the square root of negative 1 is that imaginary unit I. So we don't have a real x-intercept, right? X equals 2 plus or minus I. These are complex numbers. We don't have a real x-intercept, right? So that's why we say there's no x-intercept. So algebraically, this is how we can verify that. All right, for the y-intercept, we already eyeballed it and said that it was the ordered pair 0, 5. But if we want to find this algebraically, we can just see what f of 0 equals. And in this case, we'd have 0 minus 2 squared plus 1. Negative 2 in parentheses squared is 4 plus 1. And that's where that 5 comes from. So the 0, 5. All right, the domain of this function, any quadratic function is going to be a polynomial function as well. So the domain will always be from negative to positive infinity, any real number in the domain. And then the range, notice that whatever your y value is from your vertex, that will always make an appearance in your range. So that's why I just wrote it's related to k. For an upward facing parabola like ours, the range will be from k, the y value of your vertex, up to infinity. And for a downward facing parabola, which we don't have in this example, your range would be from negative infinity up to a maximum value of k. And you use square brackets at k because your parabola does pass through the vertex, so your y value can equal that k. So that is included in your range.